One of the big keys to success when we're talking about the conic sections is given any conic section, if you can identify the significant point, which for an ellipse is the center, the orientation, in this case a horizontal versus vertical major axis, and the significant distance or distances associated with the conic section, in this case that would be A, B, and C, then you know everything there is to know about your conic section. So we're going to start by doing exactly that. In our first example, we're looking at x squared over 64 plus y squared over 16 is equal to 1. First thing to do is actually identify that this thing is an ellipse, and the way that we can identify that it is an ellipse is that both x and y are present and squared, and they have different coefficients. X squared's coefficient would be 1 over 64, y squared's coefficient is 1 over 16. If they were the same coefficient, it would be a circle. If they're different, and it's a sum of the squares, that makes it an ellipse. So with those things in mind, let's see if we can identify all of the important things. First off, as we're looking at the x squared and the y squared, we notice that nothing is added or subtracted directly from the x or y variable. That means that we could essentially interpret the x squared as being x minus 0 squared. We can interpret the y squared as being, for all intents and purposes, y minus 0 squared. It's for that purpose that we can identify the center of the ellipse as being the origin, the ordered pair 0, 0. When we take a look at the denominators, as far as the denominators are concerned, whichever one is larger is going to take on the role of a squared. Whichever one is smaller is going to take on the role of b squared. Again, major is bigger than minor. Now with that in mind, this allows us to identify not only the values of a and b. A in this case would be the square root of 64. I'm not going to say plus or minus 8 because we are referring to a distance. Distances tend to be positive only. Excuse me. Once again, doing the same thing for b. That would be the square root of 16. Again, we don't need a plus or minus because b is a distance. C we'll be able to figure out in just a moment. And finally, the larger denominator is under which variable? Well, that would be the x variable. X is our horizontal variable, which lets me know that this thing has a horizontal major axis. This also means that extending from the center, if we were to move 8 units in the x direction, left or right, and then move 4 units in the y direction, up and down, that these 4 points together, when connected with something that looks at least a little bit round, would be an accurate depiction of what our ellipse actually looks like. As you can see, I'm not hitting any of my targets, and this is really wavy today, so apparently not having a good drawing day. That's fine. We also said for the ellipse that it has the Pythagorean theorem associated with it, but the Pythagorean theorem has a being the largest quantity. Therefore, we would set this up as a squared is equal to b squared plus c squared. Now, a squared we identified as the larger denominator, that's 64. B squared was the smaller denominator, that's 16. We can use these to calculate the value of c squared and subsequently the value of c. We'll start by subtracting 16 from both sides. That'll give us 48 is equal to c squared. Taking the square root of both sides and once again negating the fact that we need a plus or minus, we can call that the square root of 48. 48 can be factored into 16 times 3. 16 has a nice square root, 3 does not. So the value of c would be 4 square roots of 3. We'll fill that in right here. This means that starting from the center, if I were to move to the right or to the left by a total distance of 4 square roots of 3, I would arrive at the 2 foci for the ellipse. I suppose then you could also use that to calculate what the sum of the distances would be, but we're not going to worry about that here and now. Let's move on. Next example. X squared over 25 plus y squared over 49 is equal to 1. Similar to what we said for the previous one, because there's nothing being added or subtracted directly from the x or y variables, the center is going to be located at 0, 0. Once again, we can identify the values of a and b based off of our denominators. You'll notice this time, though, that the larger denominator is actually under the y variable. That means that under y squared, we'll see the value of a squared, and under x squared, we'll see the value of b squared. That allows us to calculate our value of a as being the square root of 49, and b as the square root of 25. Those turned out nice. That also means that we'll be able to get the value of c in just a moment, similar to what we did above. Now, because our larger denominator is under the y variable, y is our vertical variable. This means that we are going to see a vertical major axis associated with this. That also means that if we were to start at a center, if we go 7 units up or 7 units down, we would arrive at the two vertices. And if we were to go 5 units to the right or to the left, then we would arrive at the two co-vertices. Then drawing something at least a little bit round, passing through all these points. Oh no, the lights are going out. Oh no, the lights are going out. Okay, all better. That would give us the general shape of our ellipse. Now, with that in mind, once again, if we are interested in the value of c, we would set up our Pythagorean theorem once again. A squared is equal to b squared plus c squared. Value of a squared is 49. Value of b squared is 25. We get those directly from the denominators. Once again, to solve for c, we subtract the number associated or paired with c squared on that side. We get 24 is equal to c squared. And taking a square root of both sides, we get c is equal to the square root of 24, which again simplifies pretty nicely. 24 is equal to 4 times 6. 4 has a nice square root, 6 does not. So our value of c would be 2 square roots of 6. We'll put that right here. Because we have the vertical major axis on this one, that means that starting from the center, if we were to go up or down 2 square roots of 6 units, we could arrive at our two foci. Everything here is being eyeballed and approximated. I hope that it still conveys the point. Finally, one more example, because we've had 2 back-to-back examples where the center was at the origin. I submit to you this one. This one will be a little bit more complicated. Here we have x minus 5 quantity squared over 64 plus y minus 4 quantity squared over 36 is equal to 1. Once again, we'll start with the center. The center in this case, we do see that there is a number being added or subtracted from the x and y variables. We talked about this for the circles as well. If you want to get into the mindset of set what's inside equal to 0 and then solve for the associated variable, you'll be able to get your center no problem. Solving the first equation, we get x is equal to 5, and the second equation gives us y is equal to negative 4. This means that our center will occur at the ordered pair 5, negative 4. Our distances we can get from our denominators. The larger denominator represents a squared, and the smaller denominator represents b squared. In this case, the larger denominator is 64. That'll be a squared. The smaller denominator is 36. That'll be b squared. Taking the appropriate square roots of each of these quantities, we will get that the distance a is 8. The distance b is 6. C we'll figure out in just a moment. As far as the orientation is concerned, the larger denominator is under the x variable. X is our horizontal variable. That lets us know that we will have a horizontal major axis. To get our value of c, we'll set up our Pythagorean theorem once more. Plug in the values of a squared and b squared that we're getting directly from these denominators. So 64 is equal to 36 plus c squared. To solve for c, we'll do the same as we did for the last couple of examples. We'll subtract 36 from both sides of the equation. We get 28 is equal to c squared, and take a square root to finish solving for c. It's a distance, so we don't worry about the plus or minus. We'll simply call that the square root of 28 for the time being. 28 can be factored into 4 times 7. 4 has a nice square root, 7 does not, and so we evaluate each. That'll be 2 square roots of 7. Now, I intentionally gave us a little more space on this one because I wanted to talk about how to find, once we have all of this information, things like the vertices, the co-vertices, the foci, that kind of thing. So we know that our center is at the point 5, negative 4. And forgive me for not bringing graph paper, but I think that I'll be able to get everything okay. Because it's a horizontal major axis, starting from our center, if I were to move to the right or to the left by a total of 8 units, I would arrive at a vertex and a vertex. Man, I hope I made those about the same distance. It's not bad. Now this means that starting from 5, -4, if I were to go to the right by 8 units or go to the left by 8 units, I would arrive at the vertices. So if I increase the x-coordinate by 8 from 5, I'll arrive at a vertex. 5 plus 8 is 13, and because we haven't moved up or down, -4 stays -4. Similarly, if I were to start at the center and go to the left 8 units, that would be doing 5 minus 8 for the x-coordinate. 5 minus 8 is -3. So -3, -4 would be the other vertex. We also have a b value of 6, meaning that starting from the center, if I were to go up 6 units, we'll eyeball this, or down 6 units, I would be arriving at our two co-vertices, co-vertex and co-vertex. This means that I will be adding or subtracting 6 from the y-coordinate to arrive at these. So with that in mind, if we were to go up 6 units, our y-coordinate would be -4 plus 6. Because we're only moving up and we're not moving left or right, the x-coordinate stays the same as 5. The y-coordinate is increased by 6. -4 plus 6 is 2. In the opposite direction, we would be subtracting 6 from the y-coordinate, which would give us a -4 minus 6. That simplifies as -10. Then connecting these 4 points with something that is at least kind of round will give you a decent looking ellipse. Don't jinx it. Don't jinx it. Oh, I was about to say, this is looking considerably better than the last couple. Now, as far as the foci are concerned, this one's a little bit more complicated because we don't have a nice round number for our c value. Our c value is 2 square roots of 7, and starting from the center, we would have to move right or left that many units to arrive at the two foci. There isn't a great way to say that, so we'll just say 5 plus or minus 2 square roots of 7 for the x-coordinate. The y-coordinate will be the same as everything else on the major axis, and that'll be -4. Now, please don't make this mistake. This does not mean that you're doing 7 square roots of 7 or 3 square roots of 7. These are not like terms, cannot be combined. Therefore, we'll just leave it as is and call it good.